All right. Hope everybody's doing well. We've been talking about multiple regression for a little while now, and I hope everybody who's watching has watched some of those videos or understands a little bit about multiple regression, because we're going to pick up more or less where we left off. So let's see. Multiple regression, what we're doing now is we're looking at the relationship between one variable, which might be y, and more than one other variable generally. That's what makes it multiple regression. So first of all, we have our intercept term, beta 0. And then we have coefficients and other variables, regressors or explanatory variables, right-hand side variables, whatever you want to call them. But this is the kind of a typical model that we might include. So we're estimating a stochastic relationship between y, which is our dependent variable of interest, and these regressors, x1, x2, x3, as well as our error term, right? That's what makes it a stochastic relationship. Okay. Now, so far, what we've looked at has been quantitative variables: miles traveled, price, number of customers, anything you can measure with a number, right? We looked at housing and we looked at square footage, number of bedrooms, etc. And so we've been looking at quantitative data. But lots of times what we care about is, and we looked at this a little bit with goodness of fit tests, lots of times what we care about are categorical variables, sometimes called qualitative variables. They're non-numerical data sometimes. What might some examples of this be that we might care about? Well, we looked at wage equations a little bit, and in a wage equation, clearly, one item of interest is whether or not there's a gender gap. So gender might be one category, set of categories we care about. Another might be educational attainment. You might also care about method of payment. So if people pay with a credit card or a check, does that have some effect on their likelihood of purchasing something or the amount that they'll spend? School district, right? So if you're looking at housing prices, you want to categorize them by school district. If you don't, in the United States, you're going to miss something, because public schooling means that houses are very clearly priced based on the school district that they're in. Now, in some of these cases, you might be able to proxy for it, right? So with school district, maybe what you care about is school quality, so you try to include a numerical variable like score, test scores, right? SAT scores in the high school, or the percentage of people students who attain the standards locally. But some of these are harder, right? Method of payment. I mean, it's hard to do method of payment numerically, right? It's hard to do gender numerically. So this, should we care? Do we care? Well, we might care quite a bit. And I'm going to use an example of made-up data that I built to show you an example of when this should really be concerning. Okay, so I made up some data, and what we're looking at here is we're looking at apartments. We have data. These are apartments. Recent rentals is what I'm calling it. So we have recent apartment rentals, and clearly these are made up, but they're indicative of the underlying pattern that we might care about. What we have is we have rent, and we have floor space, and we have the city here, which I didn't type in here, but okay. Now, what do we get? Well, if we plot this data, we can just do a scatter plot to start, to kind of see what this looks like. And this data, if you look at it, looks like this. Now, what you're seeing here is from the underlying data, we have square footage, and in Little Rock you have larger square footages, and we also have rent, and in New York you have much higher rent. What that means is that we in the scatter plot, you can see we have New York properties and we have Little Rock properties, Little Rock, Arkansas. Right? So these are LR apartments, and these are NY apartments. And this is the model. Let's just say we wanted to know what the effective floor space is on rent. Well, using what we already know how to do, it would look like this, right? We'd have rent is a function of an intercept term plus beta 1 times floor space. And then our error term here. And that's our model, right? The problem is that if we estimate this model, it's bad. Let's just put it that way. What happens is we have this line right here. That's our estimated regression line that you get. And that's not good. That's not a very It's not a line you like to see. The reason is this. Two things. One, we have a misleading r squared. Our r squared says is a 0.602, which is pretty high. I mean, that's a pretty decent fit. But the other problem is that B1 is less than 0. What that says is that floor space decreases rent, right? More floor space decreases rent. There's a negative relationship between floor space and rent. We don't think that should be the case, right? There are sound reasons, sound analytical reasons to think that that shouldn't be the case. So what's going on here? Well, the problem is that we have floor space correlated with city, right? What Little Rock has bigger apartments, and that means that our estimate B1 soaks up city, soaks up the effect of the omitted variable. So that negative B1 is really saying that, well, bigger apartments rent for less than smaller apartments because they're in different cities. We're not including that, and so our estimate of the relationship between beta 1 and between floor space and rent. Sorry, our estimate of that relationship is negative because it's capturing something else. It's not the floor space that's driving it. It's the differing cities. Now this is bad because what we have a case of a biased estimate of the coefficient. And when you have a biased estimate, that means that it doesn't matter how much data you get, right? It's not imprecision. It's not that, it's getting more data is just going to make it worse because it's going to make us think that we have a better estimate than we do, because it's going to tighten the precision on that. It's never going to be correct. The reason for this is that we have a model misspecification. Our model is misspecified, meaning that when we set our model up here, we said, well, rent is just a function of floor space. We omitted a very important variable that should have gone into that model. That is part of the process of determining rent. What we did was we failed to include a variable. And so this particular type of bias is known as omitted variable bias. It's hard to catch. You got to be attentive to the building of your model if you're because it might not, usually it's not going to, this is pretty clear cut, right? We have two sections and they're very separated. That's because it's made up data. In practice, a lot of times it doesn't look like this. And I recommend taking a look at the restaurant ratings example in the playlist to see what happens when you have a very different, or when the scatter plot doesn't look quite so transparent. Sometimes you have to take a guess. Okay, now the way to solve this problem is pretty straightforward. What we do is we just include the omitted variable. So we want to include a city in our model. But how do we do that? What's 3 plus New York? I don't know. It would kind of be a hard problem if somebody else hadn't already solved it. Fortunately, somebody has solved it. And this is what we do. We're going to create a type of variable called a dummy variable. And a dummy variable looks like this. I'm just going to define a general dummy variable. Dummy variable, where'd my pen? There we go. D sub I equals whatever. 0 if an observation isn't something. If it isn't a credit card transaction, or if it isn't a New York City apartment, or what have you. And 1 if an observation is. What does that mean? Well, let me explain it a little bit further. Let's create a dummy for our particular use. I'm going to create a variable called NYC dummy. And this is how we define it. NYC dummy is going to be a variable that we're building that's 0 if not a New York apartment, and 1 if it is a New York apartment. Easy enough definition. What this allows us to do is we can now extend our model. Let's extend our model to include the dummy variable. So our model before included this rent equals beta 0 plus beta 1 times floor space. But now we're going to add our dummy variable plus beta 2 times NYC dummy plus epsilon. And this is a different model, right? Now we're incorporating the fact that we have the city, that these come from different cities, into our model. When we run the regression to estimate this model, we'll get something different. Okay, this is what the new model looks like, including the old line in there. So this downward sloping line was the old estimate. But here, these two lines, they both have the same slope, but they have different intercepts. So the slope on these lines is the same. What's the slope? Well, if you estimate it, hold on, review, let's get our pen back up here. B1, our estimate now, is 0.588, which says essentially that with every additional square foot, rent goes up by 58 cents, something like that, if that makes sense. I don't know if that makes sense, but it's made up data, so just roll with it. But what we've done essentially, so by our model, we've essentially said that it doesn't matter whether you're in New York or you're in Little Rock, floor space has the same effect on rent, right? Because floor space is only related to rent through beta 1. But what we've essentially done is we've shifted the intercept term, right? The estimated intercept for Little Rock, in this case, is B0 plus B2 times 0, because NYC dummy is always 0 for any Little Rock apartment, which is going to be just B0, which equals 127.55. That's what the estimation gave me. For New York, however, we now have an intercept of B0 plus B2 times 1, which equals 127.55 plus 1988, which equals 2,116 roughly. So let's look a little bit more at this interpretation. B2 then becomes sort of an estimate of the markup for living in New York. And when we have a model like the one I built, what we are essentially doing is we're assuming that there's a fixed relationship between floor space and rent, but then there's also like a fixed markup for living in New York. So let's look at it. We had the model above. I'm not going to show it again, I don't think. But what we can do is come up with two situations, right, from our model. So our expected value of y from the model in Little Rock is equal to beta 0. That's a beta. You can tell that, right? Beta 0 plus beta 1 times floor space, which I'll just write x1 for space, plus beta 2 times 0. And that's the expected value, so we don't have an epsilon, which means that it's just equal to beta 0 plus beta 1 x1 floor space. And that is, if we know we're in Little Rock, that's the expected rent. Our expected rent is just it's just going to be their intercept term plus the coefficient on floor space times floor space. What happens when we look at an apartment in New York? Well, on average, a New York apartment is going to look like it's going to have this as its conditional mean function. The same thing as Little Rock, right? Plus beta 2 times 1, right? Which means that this is just a fixed bump up, right? Now we can rearrange these terms if we want. It's going to be beta 0 plus beta 1 x1 plus beta 2, which again is now just going to be a constant, which means we can put the constants together, beta 0 plus beta 2 plus beta 1 x1. Now in both cases, we just have one slope term, right? Beta 1 x1, beta 1 x1. But now we have two different intercepts. This is our intercept for Little Rock, and this is our intercept for New York. And in our drawing, you can see that that's what this looks like in our scatter plot with a line. But essentially what we've done is we've taken the regression line, that should intersect actually at 2116, that's pretty close. This one's going to be way off because I'm not that good at drawing, but it should pop right at 100 or so. There we go, not bad. So now we have two lines with the same slope. The slope in both of them is B1 for every one unit increase in square foot. You get a B1 increase in rent, but you'll also have this difference in intercepts of $1,988. Okay, so the coefficient on our dummy variable accounts for the overall difference on the mean monthly rent between New York and Little Rock, controlling for the difference in floor space. If beta 2 is positive, then the average rent for the same floor space will be higher in New York than in Little Rock. If it's negative, then the average rent will be lower. Clearly, it's going to be higher in this case. Yeah, I recommend that you take a look at 1537, which is the restaurant ratings example, to take a closer look at that. Where there we look at whether restaurants that are Italian food get better ratings over seafood steakhouses and categorize those. Now, that's not all you can do with dummies, right? First of all, we can look at you can look at dummies for more than two categories, right? So that in that case, we looked at just two categories. But let's just say this is a silly example. But let's say what we're interested in whether ACT score varies by favorite color. Favorite primary color, right? So we have three primary colors. Our three primary colors are red, blue, and yellow. Okay. And we're going to estimate the following regression equation. Remember, regression equation is the expected value of y. We want to know how this varies. Well, our model, let's see, we're going to need to define two dummies. This is the way that it works. So if you have Q categories, you need Q minus 1 dummies. You can pick whichever ones you want, but the way I'm going to do it is I'm going to define D blue and D red. You don't want to have all three. If you had all three, you'd have a problem with collinearity or multi-collinearity, and then you wouldn't be able to estimate it. So you always want to leave one empty, and I'll show you what it looks like when we get there. So our regression equation is going to be beta 0 plus beta 1 times D red plus beta 2 times D blue. And that's our regression equation. What this means is that we now have our expected ACT score, given that red is our favorite color, is going to be beta 0 plus beta 1 times 1 plus beta 2 times 0. That's equal to beta 0 plus beta 1. Easy enough, right? So when we get our estimates, those are what we'll estimate for your ACT score if red was your favorite color. Now, what would your ACT score be if blue was your favorite color? Well, it would be beta 0 plus beta 1 times 0, because remember, D red is going to be our dummy for if red is your favorite color, plus beta 2 times 1, because D blue, right here, is our dummy if blue is your favorite color. Now, we simplify this. This cancels out. You get beta 0 plus beta 2 is your estimated ACT score. Last but not least, we can look at the omitted category. We omitted yellow, but we can still figure it out. What would your ACT score be if that's given? That's a let's try that again. Your estimated ACT score, given that yellow is your favorite color. Sorry if I didn't mention this. This little thing here, there's a vertical pipe, is the typographical symbol. It's just a vertical bar, and it means given that. So I may have used that in the past. If you haven't seen any videos with me, you may not have known that. So if yellow is your favorite color, then the regression equation we're estimating is beta 0 plus beta 1 times 0 plus beta 2 times 0, which is just equal to beta 0. So we always use Q minus 1 dummy variables. If we used Q, then our constant would be equal to the sum of our dummy variables, which would violate one of our assumptions. Many statistical programs will catch that automatically. But you can see that if we use just two dummy variables, we get separate estimates for each of our situations, which is what we want. Now, one way to think about this is that beta 0 is sort of a baseline. That's your score if yellow is your favorite color. And then beta 1 is the bonus or penalty for having red instead of yellow. And beta 2 is the bonus or penalty for having blue instead of yellow as your favorite color. And so if you want to interpret them, you've got to be careful with dummy variables. You really need to be comfortable building models, comfortable working with models, and get in the habit of it. Once you've done that, then you can do a lot with dummy variables. This is only one example, and you can have lots and lots and lots of different dummy variables. But you can use the dummy variable to adjust slope as well. We haven't done that yet, but I can show you what that looks like. Let's sorry, this stuff is moving around on me. I'm trying to make a little more space here. Let's look at an example of where we modify our slope quick, and then let's see what we have here. Well, we have y equals beta 0 plus beta 1 x1 plus beta 2 x1 times d2 plus epsilon. Right? Let's look at this model where d2 is a dummy variable, right? Well, what do we have? Let's look at the expected value of y when our dummy is equal to 0. Okay, when we turn off the dummy, whatever. Let's imagine that d2 is paying with a credit card, and we're looking at people who don't pay with a credit card. Well, now we have beta 0 plus beta 1 x1 plus beta 2 times x1 times 0, which cancels out. So there we just have beta 0 plus beta 1 x1, which says that the relationship between y, right, the expected value of y given d2 equals 0, the relationship between y and x1 is just beta 1, right? It's just given by that coefficient, that population parameter. Now let's look at the situation where we have the dummy variable turned on, right? This is people who do pay with a credit card, perhaps. And now we have beta 0 plus beta 1 plus beta 1 x1 plus beta 2 times x2 times 1, right? Because these are people where the dummy is on. This gives us beta 0 plus beta 1 x1 plus beta 2 x1. Sorry, this should be x1. Now, if we want to group like terms, this becomes beta 0 plus beta 1 plus beta 2, the quantity, times x1. So what we've done here, before we were shifting the intercept. When we were looking at the apartments, we were shifting the intercept term. But here you can see the intercept is the same. What we've done now is we've used the dummy and an interaction to change the slope. Right? The slope for the group that pays with cash is just beta 1. But the slope for the people who pay with a credit card is beta 1 plus beta 2. Now, if beta 2 is not equal to 0, if we can conclude that that's different from 0, then there's a change in slope between these two groups. You might use this to see if variable costs are different across different subsectors of the same industry. You might want to use this to see if men value something more highly than women. Oftentimes, for scientific purposes, dummy variables can be very helpful. So if you have a controlled randomized trial, you can define your dummy as 1 if treated and 0 if not treated. You include other explanatory variables, and if it's truly random, then the t-test on the dummy coefficient is a good test if, on average, the treatment affected the outcome. Now, this is like a test on the difference between sample means. And if you go way back to when we were doing hypothesis testing, when we were doing differences between samples, it turns out that a dummy variable and a t-test on a dummy variable will give you sometimes the same exact p-value, right? It'll be the same exact thing as doing a t-test on two different samples. All right, now there's more you can do with dummy variables. Clearly, I've showed you one example where you modify the slope, one example where you modify the intercept, and you can move them around as much as you like. You can use multiple categories. You can interact them with lots of different things. As we go forward, I might talk about some more of these. But as with any tool, the more familiar you are, the more you can do with it. So give it a try. If, we're going to have a chance to play with them with some exercises. But yeah, there's a lot you can do with dummy variables. All right, I'll be back soon to talk more about model building and and some of the stuff we can do, and other ways to check and account for misspecification in our model. If you have any questions, as always, shoot me an email at jjdelaney@ualr.edu, or leave me a comment here at EconDRD. Or yeah, I guess that's pretty much it. Hope you guys have fun, and I'll be back in touch soon. Bye.